Section 4.7, Logarithmic Scales. So this is a section that has application problems involving logarithms. Section 4.6, if you remember, had application problems involving exponential models. So section 4.7 is dedicated to the logarithm. And we're going to study three in particular. pH scale, that studies or that measures how acidic or how basic a solution is. The Richter scale, which studies or measures the magnitude of an earthquake. And then the decibel scale, which measures the intensity of sound. These are all these are all what are called logarithmic scales. Now, the reason for having a logarithmic scale is when you're measuring something, whether it's the acidity of a solution or the intensity of an earthquake or the intensity of sound, when you're measuring something that has a very, very large span of numbers. For example, the Richter scale is the magnitude of an earthquake, but what it does is it measures the amplitude on a seismograph. And the amplitude on a seismograph can be anywhere from 10 to the negative 4 centimeters all the way up to 8,000 centimeters. So that's a very, very large span of numbers. And same with the pH scale. The pH scale really is measuring the concentration of hydrogen ions in a solution. And that also is a very, very large span of numbers. And so to make the measurements more manageable and more meaningful, we take logarithms. Here's an example. Before we get to pH and Richter and decibel scale, here's an example of what I'm talking about. Let's say we start at 0 and then 10, 100, 1,000, 10,000, 100,000, and 1 million. So this is a very large span of numbers. And let's say we're measuring something that has the potential to be between 0 and 1 million. That's a very large span of numbers. So to make this more meaningful, we could put this in terms of a logarithm. As a matter of fact, let's do one small change. Let me change this to 1 rather than 0. Okay, so this is 10 to the 0 power. This is 10 to the first power. This is 10 squared, 10 cubed, 10 to the fourth, 10 to the fifth, 10 to the sixth. If we put these all in terms of a logarithm, like this. So we're taking the same span of numbers from 10 to the 0 all the way to 10 to the 6th power. But we're going to now measure using a logarithm. So log base 10 of 10 to the 0 power is 0. Log base 10 of 10 to the first power is 1. Log base 10 of 10 squared is 2, and 3, and 4, 5, and 6, and so on and so on. So what started as a large span of numbers from 1 to 1 million, when we put it in terms of a logarithm, gave us a much smaller span of numbers from 0 to 6. And that's essentially what the pH scale or the Richter scale or the decibel scale does, is it takes a set of numbers with a very, very large span. We take logarithms and produces a set of numbers with a much smaller span. So let's take a look at the first one, the pH scale. So the H plus is a measurement of the concentration of hydrogen ions in moles per liter. So I've just written the hydrogen ion concentration of some common liquids: Coca-Cola, lemon juice, milk, and seawater. And you can see that there's a very large span of numbers here: 0.000794, 0.0158, 1.99 times 10 to the negative 6. This means that you move the decimal 6 spots to the left, so you have 5 zeros in front of it. Here you would move it the decimal 9 units to the left, so you'd have 8 zeros in front of this one. So we're talking about extremely small numbers for sure, but it's a very large span of extremely small numbers. And so it was, probably, I think the pH scale came out in about the early 1900s, but someone said, you know what, there's a easier or a more manageable way of measuring this, and they developed the pH scale, which measures the same thing. It's really the concentration of hydrogen ions, but it does it in terms of a logarithm. So here is the pH scale right here. It's negative log of the hydrogen ion concentration. So for Coca-Cola, for example, it'd be negative log 0.000794, lemon juice, milk, and seawater. So this is how you would calculate the pH. And luckily, since it's a common logarithm, these are all values that can be found on a calculator. So Coca-Cola has a pH of about 3.1. Lemon juice has a pH of about 1.8. Milk has a pH, turns out to be about 5.7. And seawater turns out to have a pH of about 8.2. And again, these are all values that you would just plug into a calculator using the common log button on your scientific calculator. Now, any values on the pH scale that are less than 7, 7 is considered neutral. It's the temperature of, or it's the pH of clean water. So 7 is neutral. Anything below 7 is considered to be an acid or acidic. Anything greater than 7 is considered to be a basic or alkali. So anyway, that's the pH scale. It gives a more manageable measurement of hydrogen ion concentration than in moles per liter. Okay. The next the next logarithmic scale is the Richter scale, and it bases its measurement magnitude on a seismograph reading. So a seismograph, you can see here, the seismograph measures the intensity I of an earthquake, and the measurement it gives is what's called the amplitude of this seismograph reading. And amplitude is the measurement from the midline to the peak. So the midline to the peak is amplitude. And so that's what is considered the intensity of the earthquake, is this amplitude measurement from the midline to the peak. So a standard earthquake, one that is just barely readable in a seismograph, has an amplitude of 1 micron, or 10 to the negative 4 centimeters. So what's one that's just barely readable, or it's the intensity of an earthquake that would first register on a seismograph. There are some earthquakes that are so small it wouldn't register on a seismograph, so the standard earthquake is one that begins to be measurable on a seismograph. And that's called S. A standard earthquake has an intensity of 10 to the negative 4. That's what S is right here. And then I is that amplitude measurement on the seismograph. And that's the Richter scale. M for magnitude is log of I, the intensity, divided by S, which is the standard intensity earthquake of 1 micron. And so the magnitude of an earthquake that has an intensity of 3.75, so the amplitude on a seismograph would be 3.75 centimeters. The magnitude would be m equals log 3.75 divided by 10 to the negative 4. And this is something then that you would calculate on your calculator. This comes out to be roughly 4.6 on the Richter scale. But let's see how that compares. What about an earthquake that has an intensity of 37.5? So this is 10 times stronger, or it's one that's 10 times as intense if it measures 37.5 centimeters on the seismograph. So its magnitude would be log 37.5 divided by 10 to the negative 4. And this measures roughly 5.6 on the Richter scale. So what's important to remember here is an increase of one whole unit in magnitude. So from 4.6 to 5.6 is an increase of one magnitude, one unit of magnitude. But it really means it's an earthquake that's 10 times as intense. So this one measured 3.75 centimeters amplitude. 37.5 is 10 times as intense. So it is a much more powerful earthquake with an increase of one unit on the magnitude scale or the Richter scale. So then what would we say about an intensity of 3,750? So compared to this one here, 3.75, 3,750 is 1,000 times as intense. So make a prediction if, based on this pattern, compared from this one to this one, which was 10 times as intense, it increased by 1 unit magnitude. What about one that's 10 or 1,000 times as intense? Well, the magnitude would be log 3,750 divided by 10 to the negative 4, which measures 7.6 on the Richter scale. So that's a brief overview of how the Richter scale works. It takes measurements of amplitude on the seismograph, which can vary greatly. 10 to the negative 4 is the smallest such reading, and it can go anywhere, 3,750 centimeters for a 7.6. It can go even larger if we're getting to, a magnitude 9.0 on the Richter scale. We're talking about measurements in the 10,000s for the amplitude. So we take a large span of amplitude readings and take a logarithm to end up with a more manageable scale of numbers on the Richter scale. Okay, now decibel scale. So the intensity of a sound is measured in watts per square meter. Watts per square meter. The what's known as the reference intensity, or the threshold of hearing, a sound that's just barely audible to the human ear, is 10 to the negative 12 watts per square meter. So this is an extremely very small number. 10 to the negative 12 means you move the decimal 12 spots to the left. So it's going to have a bunch of zeros in front of it. So that's the reference intensity. So I've got some different sounds here. A whisper has an intensity of 10 to the negative 9 watts per square meter. Just ordinary traffic is about 10 to the negative 5 watts per square meter. A rock concert has an intensity of 1 watt per square meter. Again, you can see this is a very large span of numbers. They are small numbers, but 10 to the negative 9, 10 to the negative 5th, and 1. It's a very large span of extremely small numbers, kind of like the measurement of hydrogen ion concentrations. But when we start to measure those in terms of logarithms, so here's your decibel scale, 10 times log I divided by I sub 0. This is that reference intensity, which is 10 to the negative 12. We start to measure the intensity using this logarithm scale, and we can start talking about decibels. So for a whisper, the decibel reading would be 10 times log. The intensity is 10 to the negative 9 divided by 10 to the negative 12. Now when you're dividing terms like this, 10 to the negative 9 divided by 10 to the negative 12, when you're dividing terms that have the same base, remember you subtract exponents. So here's what I mean. 10 to the negative 9 divided by 10 to the negative 12. If you subtract exponents, it's 10 to the negative 9 minus negative 12. You just subtract the exponents, and that equals 10 to the third. So these actually you can do without a calculator. I mean, you're welcome to use your scientific calculator, but since we're dealing with base 10 numbers usually and log base 10, some of these are pretty easy to do by hand. So this turns it to be 10 times log of 10 cubed. Log base 10 cancels the base 10 there, and we get 10 times 3, which is 30. So a whisper registers as 30 decibels. For ordinary traffic, it's 10 times log of 10 to the negative 5 over 10 to the negative 12, which is 10 times the log of 10 to the 7th power. And again, log base 10 cancels the base 10 there. 10 times 7 is 70 decibels. Your rock concert would be 10 times log 1 divided by 10 to the negative 12, which is 10 times the log of 10 to the positive 12. Log base 10 cancels base 10. 10 times 12 is 120 decibels. So getting up into that range, you can start to do some damage to your eardrums. Anything, 120, 130, 140. Getting up in that range can be damaging to hearing. So anywho, that is an introduction to the decibel scale. Here we have the Richter scale, which is another logarithm scale, measures the magnitude by taking the logarithm of the intensity of an earthquake. And here we had the pH scale, which the pH measurement is a logarithm of the hydrogen ion concentration in moles per liter. So those are three of the more common logarithmic scales used to in applied logarithm problems.